Hello everyone, let's start today's topic. In my last video, I explained you about the linear region of the IT versus VTS characteristics. So today I will explain you about the upper part of the linear region as well also the saturation region. That means last time I just told you that we did the video, this one, it was one at that time VDS is small. So today what we will do, we will increase the VDS from small to large. Okay. So last time I calculated the current ID is equal to mu n capacitance COX and the channel width length and the VGS minus VT the VDS. Here we also can tell VGS minus VT is equal to VOV, the overdrive voltage, right? We already explained you this one in my last video, VOV. So today what we will do, we need to increase the voltage, okay, and then need to check what will happen. First, just think of it like this. Suppose there is no VDS, okay? Suppose there is no VDS. If there is no VDS, then what is the gate to drain voltage? VGD. VGD is equal to VGD is equal to VG minus VD. Or we can write down VGS minus VDS. Why? As VS will cut and then VG minus VD. Okay. When I didn't connect any voltage source on the drain terminal, that means VDS is equal to 0. Or we can say when the VDS is small, then we just think about this VG is equal to VGS. This one. So when I calculate the current in my last video, at that time we considered that the VGD equal to VGS. Why? As I already write down as if VD sorry as VDS is very small, so we can just just remove that one or negate that one. Okay. So today what we are doing? Today we are doing increasing the VDS. If we increase the VDS, then what will happen? Then the VGD is equal to VGS minus VDS. Okay. Or we can write down VGD is equal to V overdrive minus VT minus VDS. Okay, you know, right? The V overdrive is equal to VGS minus VT. So if from here I can write down VGS is equal to V overdrive plus VT. So I just put this VGS value in this equation. So here you can see VGD is equal to V overdrive plus VT minus VDS. That means if I increase the VDS, then what will happen? Then the gate to drain voltage will decrease. Okay, so I will explain you what is happening here now. So just now for the sake of simplicity, just focus into this one. This is the n-type semiconductor and this is the p-type semiconductor. Okay, and you are applying a voltage source on drain to source terminal. Source and substrate is connected. That means you are connecting a voltage source here in the drain terminal and directly to the substrate terminal. So we can consider this one as this is a n-type, this is a p-type. N-type is what? N-type is the drain. N-type is the drain and p-type is what? P-type is the substrate. Okay, and now you just connect a voltage source. Okay, so here you can see this is a positive terminal of the voltage source, this is a negative terminal of the voltage source. Positive terminal of the voltage source connected to the n-type semiconductor and negative is the p-type semiconductor. That means what will happen? No current will flow from this one. We know this one, but in the meantime the depletion region will form and it will increase. If I increase the voltage, then what will happen? If we increase the voltage, then depletion region will start to increase. Okay, so now let's see. When the VDS is small, when VDS is small, when VDS is small, at that time, as I already explained you, VGD in this terminal, VGD is equal to VGS as VDS is small. So there is no such effect that it will increase the depletion region as it's negligible. But when you increase the VDS, what will happen? This depletion region will start to increase. So now total depletion region will be this area. So this red area will be depletion region. Why this area depletion region increase? As we apply a positive voltage source on the n-type substrate. It's act as a diode in a reverse bias. So it will increase the depletion region. If the depletion region increase, what will happen? The channel for the current flow, and I already explained you that the current flow from here to here, right? So that means electron flow in this channel. So that means the channel is tapered, okay? The channel is tapered. So that means the channel width will be lower here. So I will explain you how this will affect the current. But maybe in your mind, one question will be there: why this side the depletion region is the same? Why this side depletion will not increase? Why? As you can see, the source and the substrate is connected together. As the source and substrate connected together, so the voltage source between the source to substrate, that means the V is equal to the V difference is equal to V source minus V substrate is equal to how much? 0, as both are connected together. So that means no voltage is applied between this n-type semiconductor and p-type semiconductor. That's why the depletion region is not increased. But here we increase the voltage between the drain terminal to substrate terminal. That's why this depletion region is increased. Okay, so I think you understand the concept. First, the important thing is you need to understand the concept, why the depletion region increased, and why if we increase the VDS, why the current, just like last time I showed you, right? This is the ID versus VDS. So why if we increase the VDS, why the current is ultimately saturated? But when the VDS is small, you can see it's a linearly is increasing. So why is happening? This is the main reason. Why? When the VDS is small, when the VDS is small, at that time you can see the depletion region is not that much. But when we increase the VDS, what will happen? At that time, the depletion region is increased. So as the depletion region increase, the channel width is decreased. This is also called the channel width modulation. And you understand? In FET, what will happen? In FET, we increase the voltage in the gate terminal, and that one is modulating the channel. But here, we need to increase the voltage of VDS. Then the channel will modulate. Okay. Now let's go to the equations. Okay. So now, so this is the drawing where you can see the depletion is already increased, right? And the channel, last time the channel is this one, so that means channel width is decreased. Okay, so here I will draw two diagram. First diagram I will draw thing. This is the source terminal, this is the drain terminal. Okay, and this is the gate terminal. So we are thinking this whole channel, this voltage is VGS. Okay, and you already know, right? The VT is the threshold voltage such that the channel can be created. So I think that VT is this much. Okay, this voltage we need, this voltage is VT. Okay, and this will be VGS. So what will happen? This will be V overdrive. Why? As V overdrive is equal to VGS minus VT. Okay, I think you already understand this concept. Okay, now let's think. So this is the gate, this is the drain, and let's think VDS is 0. Okay, so gate to drain voltage is the whole one, that is equal to VGS. What I show you at that time, VGD is equal to VGS when VDS is approximately equal to 0. Okay, so you can see the channel will be, I will mark as a green one. So the channel will be this one. This whole will be the our N channel in the drain to source terminal. Understand? Now I will draw another diagram. Now I will draw another diagram. Now let's see, this is the source, this is the drain, this is the gate. So this will be the same like last time, VGS, okay, and this will be VT. This will be VT, threshold voltage, and this will be V overdrive voltage. Now just let's change the color, and now let's see. Just you can see here, right? As we increase the VDS, then what will happen? The depletion region increased, so the channel width is decreased. So I will do the similar thing here. So let's see. Then this is the new channel when we increase the voltage. So that means this is the VDS. Okay. Then what will happen? This will be the VGD. Why? As VGD is equal to, from here you can see VGD is equal to VGS minus VDS. So VGS is the here from, you can see, from here to here the VGS, and from here to here the VDS. So this much will be what? This will be VGS minus VDS. Okay. So that means if I try to take the average of this curve, okay, so here this is a, what is the length of this channel is L. I already explained in my last video, the length of this channel is L. So that means here will be, this will be L by 2, this will be, this will be L by 2 half, okay, and this will be L. Okay, so in this point what is the voltage? If I want to try to take this one, this will be VDS divided by 2. Okay, now I want to calculate the voltage of this one. Why? This is the channel. Now our channel is this one, right? And I need to calculate the voltage across this channel. As in my last video, I explained you that last time there is no VDS, right? At that time, the channel is this one. The channel is this one. That's why in the charge formula we put VOV into capacitor. This voltage. Why? The VOV is the whole voltage here. The VOV is whole voltage here. The in this across the whole channel is the VOV. But here you can see now the channel width is change. As the channel width is change, now I need to calculate the average voltage across this channel. So I need to know the voltage value of this one. So you can see here. So now let's see. So what will be the value of this one? It will be VTS by 2. Okay. In this from here to here will be the VTS by 2. Okay. And here to here is how much? VOV minus VDS. Okay, so in that much, this will be VOV minus VDS, and this will be VDS by 2. So I can write down the effective voltage now is equal to VOV minus VDS plus VDS by 2. So is equal to VOV minus VDS by 2. Okay, so now you understand when the channel is tapered by the depletion region, at that time the effective voltage across the channel is VOV minus VDS by 2. Now I will explain you how the current equation will change. So let's see here. Last time our channel is this one, right? That means no depletion region with tapered the channel. That means the channel is the total width is the W and length is L. At that time, the voltage across the channel is VOV. Where is VOV here? This is VOV. Okay, this is VOV. So now what is happening? The voltage across this channel is changed. And now the effective voltage is how much? VOV minus VDS by 2. So what I need to do, I just need to change the voltage. That means the equation will be same. ID is equal to mu n multiplied by capacitance of the oxide capacitance per unit area multiplied by W by L. W is the width of the channel and the L is the length of the channel multiplied by here I need to, what I need to write down? I need to write down the effective voltage. What is the effective voltage? Effective voltage across the channel is VOV minus VDS by 2. VOV minus VDS by 2 multiplied by VDS. Okay. So only thing is that is the concept. If you understand the concept, you will easily understand why the current equation changed to this one. Okay. So I can write down ID is equal to mu n VOX W by L VOV multiplied by VDS minus VDS by 2 whole square. Now I think you can easily understand why the current, okay, okay, so I just copy this one. So now you can see here why the current, sorry, why the current ID will change when we increase the VDS. Okay, so let's write down the equation again. ID is equal to mu n VOX W by L VOV minus VDS by 2 multiplied by VDS. Okay, now let's assume VDS is small or VDS is 0. Okay, when the VDS is small, we can easily neglect this part, right? When the VDS is small, as VDS is small, that means VDS by 2 is that too small. Then the current equation ID will be mu n VOX VOV into VDS, and VOV is equal to how much? VGS by VT, VGS minus VT. Okay, so VT is constant. So for a particular voltage of VGS, if we increase the VDS, then it will be increased linearly. Use the red color here. Okay, you understand? It will be linearly. But now what will happen? Now the situation will change. Now you increase the value of VDS. So if you increase the value of VDS, then what will happen? Then the resistance of this channel is increases. So the current will make a slope. It will not increase linearly. Okay, it increase in the slope. And this one is called completely is the linear region. Okay. Again, after that one, if we increase the VDS furthermore, what will happen? This channel will increase more. And there will be one point when we can tell you the pinch of voltage. Okay, that's the pinch of point. That means the channel, this channel will be so much low. Okay, and then after that VDS, after that, if we increase the VDS, the current will not change anymore and it will be constant. Okay, you understand the concept? So this part is the linear region, this part is the linear region, this part is the linear region, and this part is the saturation region. Okay, so this will be saturation region. So in the saturation region, what will happen? The current equation. Let's define. I will draw the same thing. just the channel. You need to draw the same thing in the exam, otherwise you will not get any marks, I think. As if you just write down the equation, changing the voltage from VOB to VOB minus VDS by 2, no one will understand why you change the voltage. Okay, so this will be VGS, this will be VT. Now we increase the VGS, we increase the VD such that the channel is tapered to this much. Okay, that means here is very small gap will be there for the current flow. Is not exactly the zero. Okay, so now what will happen? This is the VDS, and now you can easily understand this is the VOB, right? So when the pinch off condition will come, when VDS is equal to, or when the VDS is greater than equal to VOB. If the VDS greater than equal to VOB, then the MOSFET will be in the saturation region. Okay, and here what will be the average? Sorry, let's see, this is the average. So this will be VOB by 2. Okay, so this will be the same, VOB by 2. So that means the average voltage across the channel is VOB by 2. So what I need to do? I just need to, from this equation, in this equation, what I need to do? In this equation, I just need to replace this part with the VOV divided by 2. So now the equation will be ID is equal to mu n COX multiplied by W by L to VOV divided by 2. And VD is equal to VOV, as I already explained you at the saturation region. So it will be VOV. So final equation will be Cn COX W by L multiplied by VOV by 2 whole square. So this will be the current equation for the saturation region. Okay, so I think you already understand. So I write down equation 3. Okay, this one is the equation 2 and this one is the equation 1. So here I divided 3 things. This will be equation 1, this will be equation 2, and this will be equation 3. So now you can easily understand why the curve, why the MOSFET behave like this, and why the curve is from here to here is linear, from here to here is parabolic, and here to here is saturation. Okay, I think you easily understand this concept if you see my last video. Okay, but if you're new in my channel, maybe please just go to that video and just check that one first. After that, please just see this one. Okay, so this is the whole concept of the MOSFET current and how the channel is formed, how channel is tapered, okay, and how the what is the value of the current in the saturation region. In the saturation region, the point is a pinch off, okay. The channel is a pinch off, but it's not the zero. Current is not the zero. Keep in mind, okay. So we need to find out the voltage or current with this diagram. And whenever you draw the whenever you derive the equation, at that time you need to draw this one and also this one and this one. So this one will be for what? This one will be for linear, this one will be for the parabolic, or just the saturation to linear in that part one, and this one will be saturation. Okay, okay, so now I will go to the next part. Next part is this is the last part. What I need to do, I just need to calculate the conductance with the drain conductance, transconductance, and the drain resistance.